So let's look at applications of partial derivatives. I do have another video that just talks about interpreting partial derivatives, but this one is just going to be on like looking at cost. So the cost function of xy, we're going to say x is the standard number of standard units, y is the number of luxury units. So if they write it as like c sub x of xy, that means the partial derivative of our cost function with respect to x. And again, when we take the derivative of cost, we call it the marginal cost. But we're going to have technically two different marginal cost functions. One is with respect to x and one is with respect to y. So if it's with respect to x, it's going to be the change in cost due to a 1 unit increase in the product of standard products, okay, or it's 1 unit increase of x, while the production of deluxe products stays the same. So when we're taking the derivative cost with respect to x, we're saying that x is changing from, x goes from x to x plus 1, and y is staying the same. Okay, remember when we talked about marginal cost, we said it's the cost of producing one more unit. Okay, or increasing our production to 1 unit. So the marginal cost with respect to y is the change in cost to a 1 standard increase in the product of deluxe items, because that's my y. So cy is when we're changing from y to y plus 1. But while the production of the standard unit stays the same, so x would stay the same. Okay, and same thing for marginal revenue, marginal profit. It is increasing either the x by 1 unit and keeping the y the same, or increasing the y by 1 unit and keeping x the same. Okay, so again, an example from the packet. So a company manufactures 2 models of MP3 players. The cost function for producing X model 1 and Y model 2 MP3 players is given by the C of XY. Find the marginal cost. Okay, and they wrote it this way instead of with the C sub X and the C sub Y, they used the delta notation, so delta C over delta X. And delta C over delta Y when X is 120 and Y is 160. So again, when we're doing these, when we need to take the derivative, we always take the derivative first and then plug in our variables. Never plug them in first, or you will always get your derivative to be 0 because it will be a constant. So this partial derivative of C with respect to X, and again, the other way to write this is CX, would equal the derivative of this, and we're going to consider x to be the variable and y to be the constant. So the first thing I need to do actually is rewrite the square root as to the 1/2. And then to make our life easier with this, what you can do is because it's x times y, the only reason is because it's multiplies to the 1/2, you can make this 10x to the 1/2, y to the 1/2. Okay, now just a caution, if this was just, for example, x plus y to the 1/2, you cannot do that. You cannot distribute an exponent when there's a sum or difference in the parentheses. But if it's a multiplication or a division, you can put the exponent on each one. So this is 10x to the 1/2 y to the 1/2 plus 149x plus 189 y plus 675. Okay, now I didn't take the derivative, so this still is c. Don't write it as cx or the delta c over delta x until you're actually taking the derivative. Let me move this over so we have a little bit more room. So x is a variable, y is a constant. So I have 10 as the constant as well as y. And then I'm going to multiply by the derivative x to the 1/2, which is 1/2 x to the negative 1/2, because I subtract 1, plus 149x is 149. 189y is just a constant, so it's 0, and 675 is just a constant. Okay, and you don't have to put the plus 0. I'm just doing it to make sure that we see that what I'm doing. So this is 5x to the negative 1/2, y to the 1/2 plus 149. If I want to simplify a little bit, this is 5x to the 1/2 in the denominator, which would be square root of x, and then the square root of y in the numerator. Okay, so that's my partial of cost with respect to x. For y, okay, which again, we could rewrite as cy, is now we're gonna say y is a variable, x is a constant. So this one, 10x to the 1/2 is my constant in front. I'm gonna multiply by y, which is 1/2 y to the negative 1/2, plus, okay, well, x is a constant, so that's 0. 189y is 189, and then 675 is also 0 because that's a constant. Okay, and I'm just going to use the notation that they are using, but I just wanted to make sure you know that they could also say this cost function. So if I simplify this, I get 10 times 1/2, which is 5. And then we have the square root of x in the numerator. The y to the negative 1/2 would go to the denominator, and I have square root of y in the denominator, and then plus 189. So those are my two functions. And then it does ask me to evaluate them at 120 and 160. Okay, so again, it's easier to write it the other notation. So I'm going to have cx of 120, 160. And so I'm plugging that in. So I have 5 times the square root of 160 over the square root of 120 plus 149. And then we'll usually get these as a decimal. So we'll type this in our calculator. And because it's cost, we're going to do 2 decimal places. So 154.77. And then the partial for this one, for y of 120, 160. Is 5, the square root of now x. So 120 is in the numerator, square root of 160 in the denominator, plus 189. And I get 193.33. Okay. So again, what it means is if I'm increasing, they didn't really, okay, I guess they said, so model 1 and model 2. So if I increase model 1 from 120 to 121, but keep y the same, my change in cost, that marginal cost, is 154.77. So that's how much the cost is increasing for that, for producing the 121st item for model 1. And this one is saying I'm increasing model 2 from 160 to 161, and then that the cost would increase by that 193.33. Okay, so that's an example of our cost.